what is the resultant net force of these two force vectors being applied, the two ropes, right? Find the magnitude and direction of this force. So, first thing you want to do in physics when you have a problem dealing with forces, this is the way they teach you in university. You want to draw what's called a free body diagram. So, here's the tree, okay? Here's the tree. Got my tree, okay? Now, I've got two ropes, okay? So I'm going to, and these ropes are applying forces in two directions, okay? So what I'm going to do is I'm going to draw a rope down here. Okay. So there's the X component of my rope. So I also want a Y component. Okay. So what this is going to do, so I've got my X component and I've got my Y component. Okay. Now, we're told that get my, that our we've got 2I and we've got 4J. Okay. We've also got another set of forces, right? We've got another set of forces, which is 3I and 6J. So the way that we're going to do this is first, we're going to say what I and J mean, and then we're going to do the math. So what is this little symbol? It looks like a little that symbol right there. You could say I hat or J hat. That's the way we talk about it when we're saying it out loud. But it's just the I unit vector, okay, or the J unit vector. What this corresponds to is the X direction. I is the X direction and J is the Y direction. And then there's also K if you want Z, right? But this is just two-dimensional, so we don't have to worry about Z. So in order to figure this out, right? Because we got to remember, in there's different ways to calculate forces, but the easiest way when we're talking about net forces is to separate it into its X and Y components. Because if we separate it into its X and Y components, we can just use simple trig to get the net resultant force, right? Now, the net resultant force is going to be this and this, that green line, okay? Which is going to be like that and that, okay? So, how can we figure out what each of these green lines are? There's two different ways to do it, right? We could solve for each green line and then add them together, or we could add these together at the beginning and solve for one big green line. So I'm going to do the second one. So I'm going to say, where's my brush? Okay. So F net. Now our net force, remember, our net force is always going to be equal to the sum of all the forces. So in this case, we've got two of them. So it's going to be F1 plus F2. So that's our net force equation. Now, we can further simplify this by breaking F1 and F2 down into their components. Remember, this is F1, so I can put a parenthesis, so I'm going to put everything inside. So I'm going to say 2, oops, 2I plus 4J. So that's F1. And then F2 is 3I plus 6J. And of course, this is in terms of newtons, right? Newtons. Okay. Now, I cannot add I and J together. They're different. I is in the X and J is in the Y direction. So these don't just add together. This is as simplified as you can get it. But what I can do is I can rearrange this and I can add my I's together and my J's together. So if I rearrange it, what it becomes, F net equals 2I plus 3I plus, and I got a 4 and a 6, so it's going to be 4J plus 6J newtons. So finally, I'm going to arrive at this solution, which is F net equals 6I plus 10J. Okay? So that is my X and my Y direction. Now, in order to get the resultant net force, I don't want to give it in terms of I and J. I want to give one absolute magnitude and one absolute direction, right? This green line, it could be tilted in any, all I know is there's a 90-degree angle, right? But if I draw this arm as taller, right? If I was to draw this arm as taller, then my green line would have a different angle. Oops. It would have a different angle, which is a different direction than the first green line, right? So depending on the magnitude of X and Y relative to each other, it will shift the direction of my green line. So here's what I do. I go over here and I say, okay, 6I and 10J. Let's make a basic triangle. I've got 6I. I've got 10J. Taller, there we go. And I've got green line here. So I've got 6 and I've got 10. I can use Pythagoras' theorem and say F net, oops, F net equals, I'm saying A squared plus B squared equals C squared, right? So 6 squared plus 10 squared equals F net squared, which is 30. This is 36. This is 100. So I've got 136 equals F net squared. Now, in order to get rid, this is where I'm going to chime in. Okay, Alan. And this is 136 equals F net squared, right? What can I do in order to get rid of this squared and get just F net?
I have no idea.
What I can do, what's the opposite of a square? It's a square root, right? So I can say the square root of 136 equals the square root of f net squared. Because the square root of anything squared is itself, right? Because did you do square roots? Like 4
Nope.
squared. Well, you know how to do squares, right? A square is just a number times itself.
Just
So 4
multiplying
squared
it by
is,
itself. Yeah.
yeah, so 4 squared is 16. So the square root of 16 is 4. The square of 2 squared is 4. The square root of 4 is 2, etc. 3 squared is 9. The square root of 9 is 3, and so on and so on. So if you have a squared number, you can take the square root to get that number by itself. So what this gives me is that, let me see what the square root of 136 is. One second.
272. Oh, nope. No,
Square
that's by
root
itself. 136.
11.662.
Oh,
So the square root of 136 is about 11.662 equals F net. Okay, so this is the magnitude of F net. Oh, and you know what? I need to put the units. So the units or newtons, that's the unit for force. So F net is about 11.662 newtons. Now, the other thing I need is the direction, right? I need the direction. I need this angle theta. I need this angle theta. So I've got my magnitude, but I need the direction. So if I remember Sokotoa, right? Sokotoa, the the Indian princess that made a Disney movie after her. Um, JK, that's Pocahontas. Anyways, sine is opposite, right? Where you start where your angle is. So my angle is right here. So sine would be opposite over hypotenuse. So it's not sine. Cosine would be adjacent over hypotenuse. So it's not cosine because we don't, we could use it, but we don't know what, let's say we didn't know what F net is. The easiest way to do it based on what we have drawn here, right, without having to calculate this, is using these two. These are our two known lengths. So since we have two knowns, we can plug everything into our equation to solve for the angle. This would be tangent. Tangent's opposite over adjacent, which is what we're going to use. So we could say tangent theta equals opposite, which is 10, over hypotenuse, or sorry, over adjacent, opposite over adjacent, 10 over 6. Now, we need to solve for theta, right? We need to solve for theta. So what we have to do, the opposite of tangent is arctangent or inverse tangent, also known as tangent to the negative 1. So if I multiply both sides by tangent to the negative 1, multiply this side, tangent to the negative 1. What I get left with, because these cancel out, I get theta is equal to the arctangent of 10 over 6. And for this, you just plug it into your calculator, which I'm doing right now. Arctangent of 10 over 6 is about 59 0.04 degrees above horizontal. So if we, you know, it would be 59.0 degrees um, counterclockwise from the horizontal. Let's see, counterclockwise. Uh, from horizontal, from or 90 minus that, which is going to be like 30.96 degrees. Clockwise from the vertical, which is this. So depending on which one you want to use, it's all the same direction. But it's 11.662 newtons at about 31 degrees clockwise from vertical or 59 degrees counterclockwise from horizontal. Now, we will check our answer and then we will go over it and figure out where, confusion or questions lie. So let's go back. Let me change my share screen. Change windows. Here we go. Let's go back to the problem. I think I can click on it here. Yeah. So all the odd problems have the answer. 5i plus 10j. Did I do that? Oh my gosh, I used 6 instead of 5. LOL. LOL. I used 6.
Sad.
Well, I did 2 plus 3 equals 6. I'm retarded. Okay.
Unlucky.
Well, yeah. Other than that, yeah, that would have made it about 11 instead of yeah, because it would have been
Instead of
100. The square root.
11.66.
Yeah, it would have been like 11.1 because it's the square, and it would be 10 arctan of 10 over 5, which is 63.43 degrees. So it would have been, let's see, 63.43 degrees and square root of 125, which is 11.18. So it would have been about 11.18 newtons at 60. Yeah, I did it right. I just said 2 plus 3 is 6. So I'm retarded still. It's okay. But we did it correctly. So, hey, and this is this is actually a good example because this kind of stuff happens in physics all the time. You'll put a number in wrong somewhere and have a slightly off answer, and it's important to identify that. So this actually shows you how easy it is to do that.
A double lesson.
Yeah. So, but yeah, there's that problem. So if I go back real quick to the paint, we've got several concepts covered here. We've got the concept of vectors, which is, the x direction and y direction, the I unit vector and the j unit vector. So that's how we do multiple directions in physics. We've got the sum of forces. We've got net forces. And then we have trigonometry, right? So I'm going to draw a line here and say 5, 5, 5, 125, 25, 11.2, 5, 61 point, what was it? 11.18, 63.43. 63.43. Do you have any questions, Alan?
Nope.
And it's okay if you do. Does this make sense?
Yeah. It was
Okay.
nice
Do
to
you
see
think if
it was nice to see the process.
do you think if you were to do this, like find another problem like this again, that you'd be able to do it yourself?
Yeah, if the steps are pretty much the same. So, like you said, we just did vector summations and the respective vectors after rearranging it so that, we're not like cross adding x and y's together. And then what was it? So after you convert it to newtons squared or whatever to reduce that, it's just the number squared by itself, which gets you back to whatever like the actual unsquared version would be. And
Yeah, there's a square
then,
root. Yep.
yeah, gotcha. And then after that, we do a little Pythagoras theorem on the triangle there to get some angles. And then the important thing is to identify, are you cosigning, sining, or tangenting, which I think will be uh, the next thing I need to like learn specifically. But it seems
Oh,
pretty. This seems pretty straightforward once you know how to do it. I think I could reproduce it.
so the here, let me show you SOHCAHTOA. So
Yeah, I'm familiar with the
uh,
acronym. Like, it's just identifying it on the triangles is where I still kinda suck.
oh yeah. The easiest thing to remember and to get it right every time is just you say, "Where is my angle?" From the point of view of the angle here, because the angle's right here, this little purple curve, right?
Mhm.
Put myself right here inside this angle. Now I can say, okay, what are my known quantities? Well, I know what's opposite me, and I know what's adjacent me. Hypotenuse is always the long arm, so you don't have to get
Right.
adjacent and hypotenuse confused. Don't get adjacent and hypotenuse confused. But the long one's always hypotenuse, and the one beside you is always adjacent, and the one opposite you is always opposite. So in this case, I know the opposite one, and I know the adjacent one. Now we did solve for net, so we could have used that one. It just would have been a nastier number, right? It was easier to use these simple fractions, so I used tangent. But that's it. So that's the introduction to physics problem right there. So huh, we've covered vectors, and we've covered geometry, trig, and we've covered summing forces. So that's what you need to do just about every physics problem. You don't always have to do vectors. Vectors are just overemphasized in your first unit. Like once you get to electrodynamics, like they're only applied in so much as like the directions necessary, but like you don't even always need that. It's just important to learn in the beginning, right? So the next thing is switch back. Okay, Newton's laws. Okay, so we got forces. Now we've got number 23. This is going to be much like what you did before, just with a little bit extra problem solving. And this time, what I'm going to do is I'm going to have you walk me through how we should do it. We're going to think out loud and try to figure out how we should approach the problem, and then we'll do it together. This is like the most efficient way to learn physics. So, change my window again, go to the next paint. While sliding a couch across a floor, Andrea and Jennifer exert forces Fa and Fj on the couch. Andrea's force is due north with a magnitude of 130 newtons, and Jennifer's force is 30 degrees east of north with magnitude 180 newtons. Okay. Find the net force in component form. Find the magnitude and the direction of the net force. And then part C, if Andrea and Jennifer's housemates, David and Stephanie, disagree with the move and they want to prevent its relocation, with what combined force should they push so the couch does not move? So there's a few different things here. Okay. So first, let's solve for A. Let's find problem A. So find the net force in component form. So what do you think is the first step that we should do? Thinking back
Ooh,
to what we did last time.
ooh. Well, free body diagram. So we can do
Yes.
our vector summations.
Yes, absolutely. So that's a correct answer. We are going to, let's see, we're going to use red. So we've got FA. We got FA here. Oops. And it's what, 130 newtons. Oops. Let me get my paintbrush for that one. 130 newtons. Okay. And then we have 32 degrees east of north, which east is to the right. So we're gonna have a oops, let me get my blue line tool. Um, and then what I'm gonna do just to make this like draw an imaginary vertical here. And there's an angle here, which is 32 degrees. Okay. Now, if I was to want to convert, because here's the thing, right? Here's the thing. I have, right? I have two forces that are in different directions, right?
Yes.
So, so what they're going to do is they're going to create a net force that's like in that direction or something, right? Something like that. We're going to have an F net that's like up here. This is 180 newtons. Right. So this net force, we're going to have to figure out what its direction is. So one of the things that we can do to start with is break this thing into its x and y components, right? Because this is, remember, all forces are going to be in some arbitrary direction, but we can break them into components along our major axes. So our major axes here, since this is a two-dimensional problem, are our x and our y axis. Now the first force is just straight along the y axis, so that's easy. It's just 130 in the y direction. But this one, right, this one is a little different because it is in some arbitrary direction 32 degrees east of north. So what I can do, right, is I can take some right triangles, right, because I've got my x and y axes, right? So actually what I can do is just, oops, where's my line tool? Line tool, I can say that, and I can say that. Well, if you know anything about right triangles, right, I know that I've got a 90-degree angle here, got a 90-degree angle here. I also, since these two lines are perpendicular to each other, the x and y axis are perpendicular to each other, right? That means 90 degrees. So I can say this is a 90-degree angle. Well, if this is 90 and this portion is 32, then this portion must be 90 minus 32. So I can say this angle, I'll draw a double so it's different from this one, is 58 degrees. This is a 58-degree angle, right? Because 32 plus 58 equals 90. All right. So I want to get my x component and my y component. All I know is an angle and a hypotenuse. So I need, for my x component, I need the adjacent angle. So I'll be dealing with adjacent and hypotenuse. Now, out of SOHCAHTOA, which of the three, and I'll do it again, I'll draw it again up here. I could say, so TOA. Which of these three uses adjacent and hypotenuse?
Cosine.
Cosine. So what I can say is cosine, and what's my angle? 58. So I can say cosine 58 degrees is equal to x, or I could say I hat in this case. I'll just say I hat, right? But I like x. So I'm gonna say x over 180. Now we're dealing with algebra, okay? Because I want to solve for x, right? So I've got x divided by 180 equals cosine 58 degrees. So what can I do to get x by itself and solve for x? I would multiply both sides by 180, right? Because if I multiply this by 180, the 180 over 180 will cancel out. I'll be left with just x. So now I have 180 times cosine 58 degrees equals x. And I'll go to Wolfram Alpha real quick, and because my calculator's downstairs, so I'll say 180 cosine 58 degrees equals 95.39. Or I'll just say 95.385, I'll say 95.4, because I think the precision that they're using is one decimal. So it's 95. I'll just put x on this side. X equals 95.4 newtons. Now, what about y? Y, right? For y, I have adjacent and hypotenuse again, right? I can do that again because I'm using y and hypotenuse. So in this triangle, or I'll tell you what, let's do it the other way. I could either use cosine again and use this 32-degree angle, or I could use sine in this one that we've already used, this 58-degree angle. I could use sine here if I wanted to, because it would be opposite over hypotenuse, because sine is opposite over hypotenuse. So opposite, which is this one, that's the vertical arm, right? The vertical arm, that's in the vertical direction. So I could do sine 58 degrees equals y over 180, or I could do cosine 32 degrees equals y over 180. The two are equivalent, okay? The two are equivalent. So just so you know, sine 32 degrees. Sine 32 degrees is 32 degrees is equal to cosine 58 degrees. Okay. Because cosine and sine differ by 90 degrees. The two functions differ by 90 degrees. So anyways, which approach would you like, Alan? Would you like to use sine or cosine to solve for y?
Ooh, let's just go with the old cosine there since we already started with it.
Okay. So we'll use the upper triangle and we'll say cosine 32 degrees is equal to opposite or sorry, um ooh, adjacent over hypotenuse. SOHCAHTOA. Cosine equals adjacent over hypotenuse. So adjacent is y over 180, right? So now we have, just like in here, I'm gonna say 180 times, oops, oops, whoa, 180 cosine 32 equals y. So y, oops, gosh, y equals, and then plug this into Wolfram alpha, 180 cosine 32 degrees equals 152.649. So I'm just going to say 152.6. 152.6 newtons. Okay. So now I have an x and a y component for my second force, right? For the force of Jennifer. And I have just a y component for the force of Andrea. So for problem A, and this is problem, oops, this is A that we're solving right now. So for A, we're going, okay. For A, we're going to say F net, because that's what it's asking for, find the net force in component form. So F net equals, we're already told FA and FJ, so equals FA plus FJ, right? Oops. Which equals, what's FA? FA is 130 J hat, right? It's in the Y direction, right? So it's J hat, because I is X. You get XYZ, IJK. XYZ, IJK. So Y is J. So 130 J hat, right? And then that's FA. And then what about FJ? What about the force of Jennifer? That's what we broke down here into these two components here. So that's going to be 95.4 I
Wait, is I X
plus
or J is Y?
I is X and J is Y. Right. So since our X here on our triangle was 95.4, X is I, and then plus 152.6 J. So we've got common units here. We've got two J's. We've got 130 J and 152 J. So we can combine those into a total J. So we've got, in total, we've got 95.4 I plus 152 and 130, that's 282.6. 282.6 J newtons. And this is our answer for part A. Now the rest of it's easy since we've already solved all this. It asks find the magnitude and direction of the net force. Okay, well that's easy, right? So for B, for B, we've got a triangle. Oops. Got a triangle. Honestly.
Professor Piezo. I like it. Good morning, lads.
What up?
So we've got our 95.4 here. We've got our 282.6 here. So we need to find the magnitude and direction of the net force, which is the green line.
This is the hypotenuse.
F net. So Alan, how would you go about solving F net? We need to use what theorem?
The old Pythagoras.
Right. So we say a squared plus b squared equals c squared, right?
Mm-hmm.
So 95.4 squared plus 282.6 squared equals, oops, F net squared. Now, what do I do to get F net by itself, Alan?
Square.
Square root, right?
Mm-hmm.
All right. So if I square root everything, what I get left with is F net equals the square root of 95.4 squared plus 282.6 squared. So let me plug that into my Wolfram Alpha. Square root of 95.4 squared plus, what is it again? 282.6 squared. 282.6 squared. I've got 298.268 or 298.3. 298.3 newtons. So that's the magnitude. Now the direction, right? The direction, right? We've got two knowns up here. And I know we have three knowns. We now know all three sides of our triangle, but we just solved for this one. So technically you could use any three. Which function would you like to use, Alan, to solve for theta?
Well, dude, can we do a classic sine?
A sine. So sine is what?
Sine is going to be the opposite over the adjacent. And that's
No, no,
going,
no.
so
That would be tangent. That'd be tangent.
what?
Sine up here. Look at my see your SOHCAHTOA thing up here.
Oh, sorry. You're right. Yeah. Opposite over hypotenuse. My
Yes.
bad.
So for this theta angle, which two numbers would we use?
Okay. So hypotenuse is going to be what our F net value was.
Yep. What's
And
the
then
opposite going to be?
our opposite is going to be our 282.
Yes. So sine theta equals opposite, which is 282.6 over F net, which is 298.3. 298.3. So then theta equals the arc sine of this. Oop. So then if I plug this into my calculator, the arc sine of 282.6 over 2, what is that, 298.3? I
Yep.
get 71.3 degrees. Uh, so I get 71.3 degrees. That is counterclockwise from the horizontal. Counterclockwise from the horizontal. So I could say 71.3 degrees north of east, or I could say 90 minus this, which would be 18.7. 18.7 degrees east of north, because it would be clockwise from, so east of north, which is what they were using to begin with, right? So my final answer for B is going to be, man, I don't like that. It's not bright enough. Final answer for B is going to be this. And then what did it ask for C? If Andrea and Jennifer's housemates, David and Stephanie, disagree with the move and want to prevent its relocation, with what combined force should they push so that the couch does not move? Well, the combined force, what do you think it is, Alan?
Just the same thing in the opposite direction.
Absolutely. So it would be, 298.3 newtons, and it would be 18.7 degrees west of south, right?
Mm-hmm.
Okay. So we've got our three answers. Let me take C. We'll put C. Just get it. C. The answer would be 200. Oh, what is it? Force ds equals equals 298.3 newtons,
Dog shit force.
and then the theta angle would be 18.7 degrees
West of south. Or Yeah.
West of south. Okay. So now let's go check our answers since we've done this. Let's see if the math is math in here.
That's when
Are
they're.
we?
That's when all four of them will be like, "Shut the fuck up, Piezo, and just help us move this couch."
Okay. So let's see. Let me go back to where my stream is. Change windows. All right. Where were we at? 23. Let's check 23. 23. We've got let's change back. Wait, that's the wrong one. This one. There we go. So the answer that we received was this one. Let's see.
Nice, we did it.
Answer. Answer.
Oh, they rounded up to 90, or rounded down to 95 with I.
Yeah, 95 and 283. Yeah, they just use different precision. And then 299 at 71 degrees north of east. Yeah, okay. That's within one. Yeah, okay. And then, oh, they gave it in component form. So they just did a negative. They just took literally what we gave before and put a negative sign. Look how smart they are. So we get
dude, what I wrote was just opposite of B for C.
right.
The negative was way better though, very clean.
Right. And you know what I should do is I should go back to this other one that we did and go ahead and copy paste the answer um, like I did with that one with a screen share or screenshot just so we'll have it clean because I'm going to save these images. Answer daily double. All right. So now that we have done that, we have accomplished two separate things actually. In the first problem, well, I guess three, but we have practiced two problems now where we have covered vectors and we have covered forces. And we've also covered Newton's first law of motion, whether we knew it or not, right? An object in motion will stay in motion, an object at rest. Wait, is that Newton's first law? Gosh, I get them mixed up these days, to be honest with you. Yeah, an object in motion will stay at motion, an object at rest will stay at rest unless acted upon by an external force. Yeah, okay. I wasn't that retarded. Now, ooh. All right, number 25 is easy. So these first two problems we did were kind of long because we had to draw free body diagrams. We had to do trig. Let's check number 25. This is a quick one. So what I'm aiming to do is just to do one problem from each section, and now you have accomplished an entire chapter very quickly, right? Like, well, something like that. Uh, number 25. Ooh, this is a problem for punks. All right, change screen. Problem 25. If the sprinter from a previous problem accelerates at that rate for 20 meters and then maintains that velocity of a 100-meter dash, what will be her time? Oh, you know what? This is a two-parter. Shut up, fluffy dog. Hey, hey, you come here. Don't use that voice, or we're inside. All right. So, we have some equations that we get to use here. Okay? This one's pretty easy. Okay. I'm going to give you an equation, Alan, and see if you can solve for it. So this is going to be our equation for Newton's second law of motion. F equals ma. So one of the most important equations in physics. What are they asking you to solve for? The net external force on her. So, how do we solve for this, Alan?
Well, you take the mass of the sprinter times the acceleration.
That is super easy. So it's going to be 63 kilograms times 4.2 meters per second squared. This is going to equal, we're going to get units of kilograms times meters per second squared, which is newtons. That's newtons. Kilograms times meters per second squared is newtons. So we're going to get 63 times 4.2. We're going to get 264.6 newtons. I will be right back. Look at the problem. Look at this next problem and think about it for just a second. I'll be right back. Okay, you've had sufficient time to think about it. How would you like to start our approach to this problem? What are you thinking? What are your ideas?
All right. So, first thing, multiply 4.2 meters per second squared times 20 meters.
Okay. Okay. So, what's that going to give us?
The distance traveled to or while accelerating at that rate to get the final
Okay.
velocity.
Okay. So, I like where your head is at. You're actually correct in the approach we're going to take, but we're not going to do that exact operation. So, we're not just going to do 4.2 times 20. Because what that would give us, right, if we multiply meters per second squared times
Mm.
meters, it would give us meters squared per second squared, right? So if we then take the square root of that, we could get meters per second, which is the velocity. So that could give us the average velocity across time. And maybe we could use that to figure something out. But there's an easier way to approach this. So here's what I'm going to do. I'm going to give you some equations that you're going to need to solve this. Okay. So there's some equations. Give me one moment. Where's the hold on. From the kinematic equation set. Where are they? Okay. Here we go. The kinematic equation. So the kinematic equations, or is this big enough for you to read? Can you see that?
Yeah, that's fine.
Okay. So what we've got here is we have a set of equations that teaches us, how we can acquire a distance or a velocity based on these input parameters. Now, what we have here, right, is we have a force, right? We have a force that's being applied. And now this force is constant, right? It's constant. So that constant force is going to be applied for that first 20 meters. So in other words, constant force, constant mass, constant acceleration. It's going to give us an acceleration of 4.2 meters per second squared. So for 20 meters, right, we will accelerate at a certain rate, and then we're going to stop accelerating, right? We're going to stop accelerating, and we're going to continue going that same speed the rest of the race. So what we want to find out is a velocity, okay? We're going to want to find out a velocity, okay? So if we have acceleration and we have distance and we need to find velocity, so we've got three variables. We got velocity that we need to find and acceleration and distance that we know. Which of these four equations can we use?
Top right.
Top right, yes, sir. So we're going to say velocity final, right? Velocity final, that's what we're looking for, is the velocity after we accelerate for 20 meters equals velocity initial. So velocity final squared equals velocity initial squared times 2AD. Now, our velocity initial is going to be 0 in this case. It's going to be 0 because we're starting out at rest, right? We don't have an initial velocity. We're at rest, right? We just started the race. So what we're going to be left with in this case is velocity final squared equals 2AD. A being acceleration and D being distance. So that means that velocity final, remember what we can do with this square root? Or sorry, with this square? We can do a square root to get rid of it. So whatever we do to one side of the equal sign, we got to do to both sides. So if we square root this side, we got to square root that side, right? So the velocity final equals the square root of 2 AD, which equals the square root of 2 times 4.2 times 20, which equals, hold on, let me use my calculator. Square root of 2 times 4.2 times 20. 12.96. 12.96. And what are our units for velocity? They are meters per second. Right, acceleration is meters per second squared. Velocity is meters per second. Distance is meters. So remember, distance is meters. Velocity is distance over time. Acceleration is velocity over time, right? Change in velocity over time, right? Because when you do a delta t, it puts it over s. So it's just like m. So 12.96 meters, that's distance. 12.96 meters per second, that's velocity. 12.96 meters per second squared, that's acceleration. So that's an easy way to remember it. But this is going to be our velocity at the end of 20 meters. So our final velocity is 12.96. Now, that's the velocity we're going to travel for the next 80 meters as well. So what's it asking us? It didn't ask us for velocity, right? It asked us what will be her time for the race, her time, okay? So we know that we've got two different, what we'll call legs. We'll call the two different legs of the race. We'll use that term. We've got the 20-meter leg, and we've got the 80-meter leg, right? Because that's the second half. When she stops accelerating and she's got her speed now, she just cruises at that speed the rest of the race. We'll call that the second leg. It's very easy to figure out the time for that second leg. Do you know what we would do to find the time for that second leg? We know we've got 80 meters to cover, and we're going 12.96 meters per second, and we need to get how many seconds it takes us, right? So we would just divide 80 meters by 12.96 meters per second to see how many seconds it would take. So that's what we'll do for the second leg. So what I'll say is, so distance total equals distance 1 plus distance 2. We've got 20 meters and we've got 80 meters. Now, the time total is going to be time 1 plus time 2, right? Now, time 2 is easy. Because remember, velocity equals distance over time, which means that time equals distance over velocity. Or we could also say distance equals velocity times time. Right? This is our velocity equation. So that would mean time 2 equals distance 2 over velocity final. So we are going to take our distance, which is 80 meters, divide it by 12.96 meters per second, and we're going to be left with seconds because the meters will cancel out, and then we've got seconds left, and it's in the denominator of the denominator, which just means it's the numerator, so it's seconds. So 80 divided by 12.96 equals 6.17 seconds. So that's our time 2. Now our time 1, we're going to have to do something a little different. Okay? Because for time 1, we're going to have to solve for t, right? T is time. So we're going to have to solve for t. Now, all we have, right, is an initial velocity, and a final velocity. We have an acceleration, and we have a distance. So there are actually two different equations that you could use to solve for the time here, for time one. Do you know what they are?
The
I guess
bottom,
technically,
yeah,
yeah, go ahead.
the bottom right one for sure.
Yep, we could definitely use this one. Technically, I spoke wrong. We could technically use all to three different equations because I wasn't even paying attention. Up here, we've got this one. We've got velocity initial. We've got acceleration. We've got distance. We could use it as well. So we could use any of these three. And you know what's even cooler is that if we didn't solve for velocity final yet, because we did a separate calculation for that, we solved for velocity final. We can take this velocity final, right? We can take this and we can plug it in here, or we can plug it in here. But if we didn't have that, so say we hadn't done it yet, we could just use this equation because it only uses velocity initial, which is 0, right? So in fact, if we hadn't solved for this, we could use that one. So why don't we just use that one just for the heck of it, right? Because we could have used it from the beginning without doing any of this yet. We could have solved for the time for that first half. So we'll say, we'll put it here. The distance equals, now velocity initial is 0. So we don't care what the time is because it's going to be times a 0. Anything times 0 is 0. So that goes away. So what's left is 1/2 a t squared. Now this is where we need to do a little bit of algebra, okay? Because what we want to solve for is t. This is what we want to solve for is t. So we need to get the t squared by itself on one side of the equal sign. So in order to do that, we can do a little algebra. So remember, in order to get things from one side of the equal sign to the other side of the equal sign, we can do what mathematical operation?
Multiply.
Right. And in this case, we would want to divide by a, right? Because we need to get rid of a over here. We need to get rid of a over here. So to get rid of it, we divide it by itself because anything divided by itself is 1. And then anything times 1 is itself. So if we do a over a, that'll just turn into a 1. And then t times 1 is just t. So we want to divide by a. So we're going to divide both sides by a. So now we're going to have, let me do my little arrow here. Oop, oop, oop. We're going to have d over a equals 1/2, because the 1/2 is still there. We only divided by a, 1/2 t squared. Now, this 1/2, how can I get rid of this 1/2? What's a way I could go about doing that? Because what I want to do is I want to turn it into a 1, right? Because I want to multiply it by t and leave t the same. So what
Yeah.
I need to change this 1/2 into a 1.
Divide by itself again.
Yeah, I could divide by 1/2, right? Now, if you know this thing about fractions, dividing by a fraction is the same thing as multiplying by its reciprocal. So dividing by 1/2 is the same thing as multiplying by 2. So you could say, if I multiply 1/2 by 2, it'll become 2 over 2, which is 1. So I could just multiply both sides by 2. Or I could divide by both sides by 1/2, which is the same. Dividing by 1/2 is the same thing as multiplying by 2. So either way I go about it, it results in the same thing. I can either multiply both sides by 2 or divide by 1/2. So let's just say, I multiply by 2 because it's the same thing. So I've got 2d over a equals t squared. Now, how do I get t? Because I've got t squared right now. How do I solve for just regular old t? Remember, we've done it in the other two problems so far.
Oh yeah. Just square a square by itself or whatever.
We have to square root it.
Right.
We have to square root t squared because the square root of a number squared, t times t equals t squared. So the square root of t squared equals t. Okay? So the square root is the opposite of a square. So, and whatever we do to one side of the equal sign, we always have to do to the other. So I now I'm going to say t equals the square root of 2d over a. Now that I've got a time, which is what I'm wanting to solve for, I'm wanting to find time. I've got what I'm wanting to find. Now I just have to plug in the numbers. That's all I got to do now. Once I plug in the numbers, I'll be done. This is for T1, by the way. So T1 equals the square root of 2D1 over A. So it equals the square root of 2 times 20 over 4.2, because that's the acceleration. So that means, which equals, let me use my handy dandy calculator, square root of 40 over 4.2, 3.09 seconds. 3.09 seconds. So finally, her time for the race, I'll call it race up here instead of total. Her time for the race equals T1 plus T2. So T race we just add these two times together. 6.17 plus 3.09 equals 40 over 4.2. Yeah. Wow, that's a crazy time. 9.26 seconds. Now, I know that this math should be right. Well, my next question was going to be, does this make sense, right? Like, does our answer make sense? Because before you like give your final answer, you always want to say, does it make sense? 9.26 seconds is ever so slightly faster than Usain Bolt can run 100
I
meters.
was about to say that's like
Yeah. But, she's probably not going to be able to maintain that speed the whole time if she really did accelerate that much.
more like
So,
Andreas. Just kidding.
yeah. So let's check our answer because it should be right, even though whoever made the problem probably didn't factor in that this is too fast for a human to run. Let's check our answer. 9.26 seconds. Okay, 9.26 seconds. Let's check our answer. Go back, change Windows.
Actually, I think Hussein did 100 meter in what, 4 seconds, 4.7 or something.
It was 9.5 something. I think maybe 9.48 his fastest, or 9.52 or something like that. Let's go. Let's check our answers. So, problem 25. 9.259 seconds. We did it.
More like Andreas at that speed, dude. That's crazy.
So, these are some basic problems, but they have taught what. Let's review the key concepts we've learned. So we've done 3 problems, and here's what we've learned. So problem 1, we learned, free how to draw a free body diagram. Um, we learned that 2 plus 3 is not equal to 6.
Very important lesson.
Yeah, we've learned that this is the way that you can add vectors together, right? This is the way that we use sum notation, how we add things together. We've learned how to create a net vector out of component vectors, right? We got the x and y components. We can create a net magnitude and direction using trigonometry,
That's
right?
actually pretty cool. I didn't know about that.
So that's what we learned from the first problem. Now the second problem, we learned on we did some more practice with vector combinations, but this time, right, this time we started with two forces. We started with 2 different forces and we had to break one of the forces into its components. Right? We broke it into its components and then we took those components and added them to the components of another force to get a total set of components. And then we took that total set of components and converted it back into one net force and direction. Okay? So that was our second. So our first 2 problems taught us everything we need to know in order to be able to calculate force vectors, magnitude and direction. And then this last problem, we learned how to use the kinematic equations, right? We learned how to use the kinematic equations in order, and this is only 4 of them. There's actually one more. There's actually one more kinematic equation, which I think that maybe it's just this 4th one in a different notation. But we learned how to use these 4 kinematic equations in order to find the amount of time it took a runner to run a race, knowing nothing but how long she accelerated for. Right. So we were able to take one small piece of information, which is, hey, this chick accelerates for 20 meters and then just keeps running. How long does it take her to run the race? Right. Like we found how fast she was moving, her velocity, her overall time. So 12.96 meters per second is hauling, by the way. So they have a bionic sprinter here. Just saying. That's faster than Usain. So, but anyways, these core principles from these first 3 problems that we learned, these core principles, vector notation, summation, adding vectors, creating net forces and directions out of them, and then using the kinematic equations. These principles that we learned are the basis of your entire first unit of physics. If you master these concepts, you'll be equipped to do pretty much like half of your whole first unit. You'll learn that's about half of it. The other thing is just learning about the different types of forces and how they work with each other. Because this equation up here, F equals ma, this is going to be the equation that you use for like most of physics 1. This and the kinematic equations. These are going to be the equations that you use, and you knowing how to apply this is pretty much the whole thing. So before I go, we have um, we have done a few problems, and I think you've gotten the hang of it. I would like to allow you to use what we've learned to do one more problem. And I think you can do it all by yourself by just telling me what steps to take. So I'm going to do one more, and I bet you can get it.
Professor Piezo, thank you. I gotta go, guys. I gotta get to my interview. Wish me luck.
Later,
Good
bro.
luck, man.
Geo.
Later, y'all.
Okay. Here you go, Alan. Last but not least, Space is fake and gay. How can we use it? You got astronauts in orbit. They're apparently weightless. This means a clever method of measuring their mass is needed to monitor their mass gains or losses and adjust their diet. One way to do this is to exert a known force on them and measure how much acceleration is produced. Suppose an external force of 50 newtons is exerted and the acceleration is measured to be 0.893 meters per second squared. First, calculate their mass, and then, by exerting a force on them, the vehicle in which she orbits experiences an equal and opposite force. Use this knowledge to find an equation for the acceleration of the system that would be measured by a nearby observer. This is really just part A, because part B is going to be like using the equation from part A and just writing letters with it. But this will this will show us something here in just a second. So just, I know it seems monotonous and retarded and easy, but how would I do part A? I've got a force and I've got an acceleration. And I need to find a mass. There's an equation I could use that relates
Yeah, yeah.
force, mass, and acceleration.
So you need to get the mass right, you said? You would do M
Yes.
equals F.
Yes. Exactly.
Sorry, I was
So M
replying to something.
Oh, you're good. M equals F over A, which equals 50 over 0.893, which equals 55.99 kilograms. I'm just going to say 56 kilograms. Okay. Now, that's the mass. So we've solved part A already. Super dumb easy. Part B, by exerting a force on the astronaut, F, the vehicle that she's orbiting in experiences an equal and opposite force because she's sitting in the vehicle, right? So she's like, we're assuming that she's like, in the vehicle, she's sitting in the seat. So you push on her, you push on the vehicle. The vehicle in which she orbits experiences an equal and opposite force. Use this knowledge to find an equation for the acceleration of the system, astronaut and spaceship, that would be measured by a nearby observer. So what's happening here? What's happening is, I'm going to draw a box. Okay. I've got Miss Astronaut here. Whee! And then I've got Piston Machine pushing her, right? And she gets pushed this way, right? That's what we just measured, This is how much she accelerated. But what's happening is, if the ship, right, this whatever's in the ship pushing on her, whatever's in the ship pushing on her pushes her this way, then it's going to also push the ship back that way. Right? Because it's going to experience an equal and opposite force. And what if I push on the table pushes back at me. So the ship is going to push on her and she's going to push back on the ship. So we need to find an equation for the acceleration of the system, the astronaut and spaceship, that would be measured by a nearby observer. Right? So we need to see how much she's moving and how much the spaceship is moving, because both are going to be moving. Both are going to be moving, and they're going to be moving in opposite directions. So I'll help you real quick. We know F equals ma. Now, what F, what m, what a? Well, F of the ship equals the mass of the ship times acceleration of the ship. F of the girl equals the mass of the girl times the acceleration of the girl or the astronaut. I don't know why she's a girl this time. I just made her here. There, she's a girl. All right. But in this case, the force has to be equal on both sides. The force applied to the ship has to be equal to the force applied to the astronaut. So the force of the ship has to equal the force on the body of the astronaut. And F equals ma, so I can say the mass of the ship times the acceleration of the ship is equal to the mass of the body of the astronaut times the acceleration of the body of the astronaut. So you can see very quickly here that if you only knew, right? If we only knew how much force, was being applied, or if we only knew, the mass of the astronaut and how fast their body's accelerating, and we knew, uh, how fast the ship was accelerating, right? For this outside observer, we could use this to figure out how much the ship weighs, or vice versa. We could solve for any of these variables as long as we had the other ones. So this is useful because it allows us to not only know things about about the astronaut, but also things about the ship. So because it says use this acceleration to find an equation for the acceleration of the system, astronaut and spaceship, that would be measured by a nearby observer. So this I'm not sure what form they want this equation in. I'm guessing that it's probably okay. Yeah. So let's say we wanted to solve for a ship, because that's the form they have it in, is a ship. What would we do if we wanted to solve for a ship? This is the answer they're looking for. A ship equals what? It would be m body times a body all over m ship. That's it. So there is our answer. All right. I will take these images and save them. Okay. Thanks for participating. Okay. Word.
Thank you very much. That was
You
a
feel like you
great.
learned anything?
Oh, absolutely, absolutely, man. I can't wait to go back and do some of these myself.
I'm gonna save these
I feel
in
aptly
a
prepared.
folder.
Yes, will you save those images and send them to me for reference? 'Cause I took some. I wrote down like diagrams and wrote everything down kind of as you did, but also it's nice to have this.
Yeah.
I'm going to end this recording.
Yes, sir.